Hi, I'm Ben-Yaakov. This presentation is entitled Introduction to Motor Drive Control Part 1. This is an English version re-recorded of an in-house seminar given at IRP Systems, Ness Ziona, Israel, originally in Hebrew. The assumption that I've been making is that the audience do not have a very broad knowledge in control theory. And in fact, what I'm assuming is a basic knowledge in electrical engineering, and from that we'll go on. Also, the method that I'm going to show is unique, and it's been developed by me during the years, and it's somewhat different from what is conventional. So people with background of control will have to adjust. So what is the problem we're going to deal with in this seminar? We have a motor or any other system. We have a driver for it, in this case an inverter. And here is the controller that we do have to design. It includes a PWM modulator in this case, and then some code, some algorithm for generating the PWM according to some rule that we are going to develop. And then we have a feedback. In this case, I'm showing a speed of the motor through some conversion constant, converting, let's say, the speed coming out of a tachometer into a voltage, and then comparing it to what I want. This is the reference, this is the command, this is what I want, and generating the difference. Then the difference tells this algorithm here, or controller, that adjustment has to be made if there is a difference, and ideally you like this to get close to zero, so that what you drive here as you feed in as a command eventually comes out to be the actual speed. Now there are two issues that we have to worry about. One is stability and one is dynamic response. Stability means that I don't want the system to start oscillating and by itself and generating all sort of signals which are irrelevant to what I want the system to behave. And the dynamic response means that if I'm giving a step response, I don't want it to have a excessive overshoot, or I don't want the rate at which it will reach the final value to be too slow. The question is, why is it that we are exciting the system to get the either experimentally or analytically? Why is it a sinusoidal wave? The reason is, of course, that by a Fourier transform, any periodical signal can be described by a sum of sinuses. So that this is a universal sort of a test signal, then I can apply to a square wave periodic or to a triangular or any other periodical signal. Also, as it turns out, especially if I'm expressing the transfer function as a function of the complex or Laplace transform variable S, I can get the time response. That is, what will be the response when I have a step. So this is the reason for the sinusoidal representation. Now, I'm also using small signal because many systems are nonlinear, and this is the reason why we are using sinusoidal excitation, and this is the idea of bottle plot. Now, let me talk about zeros and poles. Now, if I have an expression in either a phasor form, complex form, or a Laplace form, then we can distinguish between some very basic elements of transfer functions, and as it turns out, most of the other elements or most of the system will be sort of a combination of these. So we have a pole. A pole is an expression in which we have 1 over, in this case, it's a Laplace transform S over SP, or J omega over omega P, or JF, and this is in the frequency expression, this is angular frequency, this is frequency, over F0. And the behavior of a pole is something like that. It goes flat up to the point of F0, F pole, it should be here F pole, and then it goes by 20 dB per decade. What is 20 dB per decade? 20 dB is 10-fold, decade is 10-fold, so it's reducing by 10 for every 10-fold of frequency, and this is again in logarithmic scale, dB, so therefore it is a straight line in logarithmic form. And then it turns out that in a case of a pole, we do have a phase shift of minus 90 degree starting at the, or it's actually 45 degree at the pole, and then it's moving in. Now, a zero is 1 over S over S0, or J omega over omega zero in angular frequency, or JF over should be over F0. And then what we have here is it's going up 20 dB per decade, and then the phase is advancing. It's moving toward, that's it, a little bit off here. It should be here. This is 45 at the breakpoint. And then, now I should also say that these straight lines are asymptotic. The actual line are sort of curved here and also here. And I'm just showing the asymptotic, the straight line put on the curve. Then we have a right half plane zero, which could happen in some systems. We usually ignore it. It's troublesome. Maybe I'll dedicate part of the seminar to it. It's really troublesome and it's causing a lot of trouble because of the phase delay that it is imposing and the fact that the frequency, the gain increases. So what it is, it's very similar to the regular zero, except that it has a minus here, okay? Instead of plus, it's a minus. Now, the absolute value here is the same, because for absolute value, you take this square plus this square, and then you take the square root. So the absolute square is the same, but the phase, because of the minus here, is then lagging. It's similar to a pole. So it's lagging here, advancing here, and as I said, it's causing a lot of trouble. But usually, at the very beginning, I'll just ignore and assume that the system has no right half plane zero. So now go to the actual feedback system. This is the feedback system. We take it, the output, feed it to the input, so it is a classical feedback system. This is a one-loop system. And the representation is something of this nature. This is the system, and this is the feedback, you might say. And K, in this case, is beta. It could be a constant, or it could be frequency dependent. For example, if you like the system to behave in a certain way, you might wish to make this frequency be dependent. Also, a sensor, a frequency or a speed sensor has some frequency response to it, and therefore this is not a constant. At high frequencies, it is in fact reducing the signal, so that this is not a constant. But let's assume it's a constant at this point, or frequency independent. Now, it can be shown, and I'm not going to develop it, that the ratio between the output and the input signals, S out over S in, could be voltage, current, any signal, could be mechanical signal, could be, could be in principle a chemical element, could be any signal that you have to handle. Well, it can be shown that this expression is A open loop, this transfer function here, over 1 plus beta A open loop. Now, let's have a look what happens as this product is changing. Now, this product, in the case of the motor, includes the motor plus the controller. And this controller is something that we design, we implement, and we make a decision what will be its transfer function. So I'm, in fact, in systems like this, I'm in fact in control of a open loop. Part of it is coming here as a starting point, and this is something I add, and this is now the product. So what happens if beta A is much larger than 1, meaning that the 1 can be neglected because it won't affect that much, and you see that this actually drops out. A open loop over A open loop drops out, and I'm left with 1 over beta. Now this is the strength of feedback, negative feedback of course, because positive feedback will cause oscillation because you are feeding the same signal. Now, why is it the strength? Because this means that whatever the system is, by properly designing the controller, making it in the frequency range that you are interested at, this beta A very large, you end up with an expression or transfer function between input and output, such that the system itself has no influence on the transfer function. Only the K or the beta here. Now, you are in control of this K, beta, make it whatever you want. So this means that you in fact can control the output independent of the characteristic of the motor in this case and the inverter, just by designing correctly the controller and of course the beta. This because the relationship depends on beta. Now let's try to understand intuitively why this is so. Now, beta A open loop is the gain starting from here, going into here, and then going back. This is called the loop gain. This is the loop gain. Now, if the loop gain is very, very large, system is stable, this would mean that in the steady state, this signal is very, very small, because if the gain is large, in order to generate this signal, which is about this input, you need very small signal here because of the large gain. Being so, and in the limit, when beta A is really very large, this goes to 0, and since this is in fact the Sin minus SF, this is the meaning of this plus minus, this means that if this is 0, then this equals to this. Or I should say this equals to this, because this is the control. Now this now relates to the S out by this. So having a command here makes this equal to the command, makes this equal to 1 over beta. And this is exactly what shows here. Now what happens if, however, beta A is smaller than 1? And this will always happen, because eventually at high frequency, because of the attenuation of the system and the frequency dependent, this number goes down and down. Then when it becomes smaller or much smaller than 1, we go back to the system. So we have first a behavior which is like 1 over beta, and then we go back to the system itself. Now, the point that this happens, it actually determines the bandwidth at which we control the system. Beyond that, we have no control. Whatever the original system was, okay, whatever the system. So we talked about the small signal, and we now understand we would like to have the loop gain very large in the operating range in order to reduce this error and making this equal to this. So let me go back to the problem. We have an inverter plus motor. We have some feedback. This is something that we want to control. So this we know, this we have to control. And we understand now that if we design it properly with high gain, then we're going to have a transfer function in the closed loop, which is basically dependent on this value here, which could be either constant or frequency dependent. Now let me now turn to the issue of instability. When is a system unstable? This is one of the problems we have to worry about. Now, why would a system be unstable? Let's assume that I have no input signal. And let's assume that somehow I'm starting with a signal that looks like this at this point. Now, if the gain here is 1, both in terms of the amplitude and phase, so I'm getting back here with the same amplitude and the same phase, this is a very dangerous situation. This is an oscillator, because we are feeding information or signal, and then we ending up with the same signal. Nothing is here, so this is sort of feeding itself, and this will be an oscillator. So this is, however, one particular point. But let's assume the following. Let's assume that SE is small, but SF is larger than SE. Let's say this is 1 volt and this is 2 volts. Somehow intuition would tell us that this is also for sure an oscillator, because you end up with a larger signal, and then this signal will then blow up and go up and increase. Well, not so. It turns out that it could and it could not. There are situations that you can have this and the output will be stable. Another question is, what happens if you start with a signal that comes out the same magnitude, same amplitude, but shifted in phase? Is this stable or not? Again, you can't tell. You have to have some tools for deciding that will help you to decide as to, or to know as to whether the system is stable or not. And as it turns out, we have a very simple tool or criteria, the Nyquist, that can help us to say when the system is stable. So now we go back to our original problem. We have a system. We have a loop gain, which is the product of all these, is now including, this is the controller, this is the inverter plus the motor, this is a sort of a feedback. And the loop gain then is this multiplication, and I'm in general expressing it as A times beta or A times B. And this loop gain is associated with the Bode plot, as we have seen before. We see that in general, the slopes could be minus 20 dB, and if you have 2 poles, then could be minus 40 dB. It might be a 0 also, so it will go up. So this will be the amplitude, and this will be the phase. I'm starting here with 180 because the feedback, negative feedback, has built in, or we assume that the signal or the system is designed as such that the signal coming back will be minus the signal coming in, this one, and this means that there is a 180-degree phase shift. And so I'm showing it here, and then due to the lags, the phase shifting of the poles, then the phase is lagging, going down and down. Usually we are not plotting it here with 180 degree, but rather like here, we are plotting it around 0 because we assume already that there is a built-in 180 degree. Okay, so now we come to the Nyquist criteria. This is the criteria that will help us to know if there is a pole at the right half plane of the complex plane, which makes it unstable, and how far are we from it, and how safe are we in terms of stability. The system is unstable if this denominator has roots in the right half of the complex plane. The Nyquist criteria is a test for the location of the roots, or in particular, it tells us if there are poles at the right half of the complex plane. And usually, in order to use the Nyquist criteria, we are basing it on a body plot. So here it is. We have a system, we have a loop gain, and this is now showing a transfer between the error signal here back to here. This is the loop gain. This is the input. This is SF, the output. We have a certain amplitude here, a certain amplitude here, and then we have a certain phase shift. So what Nyquist criteria is saying is the following. If you look at the point at which the loop gain is 0 dB is a ratio of 1. So if you look at the 0 dB point, and then you look at the phase, then you have to watch the difference or extract the difference between the actual phase at this point, at this frequency, to 180. Again, already taking into account the original 180. This phase difference is called phase margin. And what the criteria says is if you are with a phase margin, which we call it positive, that is that you have not reached the 180, then the system will be stable. That's what the criteria says. Now, the criteria is correct for systems that do not have a right half plane 0. So we are assuming that they don't have it. Also, there is a importance to how close we are to 180 degree. Now notice that 0 here is already a phase reversal of 180 degree for the negative feedback. Another 180 means that we came back to the same phase, okay? If the phase here is 180 degree plus this reversal of 180 degree, this means that we come back to the same phase. And as we already said, obviously, if the crossing would be at 180 degree, the amplitude is 1, this is an oscillator. So this is obvious. But as it turns out, we can look at the phase margin, that is how close to we are to this point, and tell some things which are important in the behavior of the system in closed loop. So let's go back again. We look at the loop gain when it is 0 dB, and then we look at the phase margin, and here this system is unstable because we call this a negative phase margin because we are beyond the 180 degree. Just as a hint for those interested, this criteria is based on the Nyquist plane, which tells us whether there are poles in the right half of the complex plane. So this criteria is not just coming out of the blue, it is based on something very rigorous that I'm not going into in this particular presentation. Now, first, phase margin is very important because, as I have said, the closer we are to 180 degree, the smaller the phase, the more we are closer to oscillation. And it shows itself in the following. In a system that has a small phase margin, if I give a step input at the very input, that is here, then the output will have an overshoot and some oscillation. Also, if I plot or look at the transfer function between input and output in closed loop, I'm going to see at this point a hump which is indicative of the system being on what we say high Q, or actually it is sort of behaving like a second order system, and this is actually associated with this oscillation and overshoot. And the overshoot and this hump on this Q, on this increase in gain, is a function of the phase margin. At 60 and above, we just don't see oscillation and we don't see this humping. At phase shifts beyond, smaller than that, we can see some of these. Now, it's a mistake to think that we don't want any overshoot, because if you have a phase margin which is very large, say 90 degrees, then the system will be bound to be a little bit slower. The reason is that in order to get a phase margin which is large, like say here, if the cross section will be here, then this means that you'll have to design the system such that the gain, beta A, will be at this point, will be 1. So this will be the end of the band of the feedback. And beyond that, you have no control. So it will be a narrower bandwidth. So this is why we don't want the phase margin to be too large, the phase margin to be too large, but then we want it to be too small. And 40, 45 degrees is considered to be a good point with a slight overshoot, which is okay. Now, as I've said, all this is correct for minimum phase systems. And the reason is, again, that with a system with right half plane 0, the behavior of the phase is not the same, and so we leave it alone for now. We'll go back to it later on. Now, as it turns out, that if we know that the system is minimum phase, as such is the name for it, that is, minimum phase means that it has no right half plane 0, it turns out that we can tell a lot from this curve. We really don't need the phase at all. Just looking at the amplitude, we can tell whether the system will be stable, looking at this cross section of the gain with 0 dB. And why is that? The reason is that the closed loop expression can be broken into, let me go back here, into zeros and pole. This is taking all the expression for the transfer function, and then multiplying, and then we end up with something like this. The complex or phasor form, which is shown here. Now, this is a 0, this is a pole. We have many zeros, we have many poles, and what happens is that each of the 0 is causing an increase associated with a phase advance of 90 degrees. Then we have maybe a pole that is reducing, which is reducing the phase again, and since the pole is now, this is going up, the pole is going down, the end result is a straight line. And then we have another pole which is causing a decrease in gain, and there will be another phase shift of minus 90 degrees, and then we have another pole here, and it has another phase shift of minus 90 degrees, but now the rate here is minus 40 dB per decade, because we have actually two poles here. And now we have here a 0, which brings it back to 20 dB, because the 0 is increasing, and the phase now is also subtracted, and the end result is that history does not matter. That is, if you look at this section here, and you see that it goes down 20 dB per decade, the fact that this went up and down with phases that are advancing and delayed does not affect this portion here. And you know that since you got already to this behavior of 20 dB per decade, this means the phase shift at maximum will be 90 degree. And if this phase shift is 90 degree, then the phase margin, if it is 90 degree already, the phase margin will be 90 degrees, because 180 minus 90. So the point is that it's enough to look at this area here of the cross section and to look at what we call the rate of closure here. If the rate of closure is minus 20 dB per decade, you're good. You don't have to worry what happened here. This is very powerful, which means that you really don't have to do any complex analysis of the system. You just look at this area here. Let me now go one step ahead. And the question is, how do I approach the design of the controller? Now in the system, in any of the systems that I've shown and in practical, we have two parts. We have of the loop gain. We have a part of the loop gain that is known, and the part that we have to design. This is the controller. It's always. Each one of these can be a complex system, many poles and zero, etc., many blocks. But at the end of the day, we have something that we know, something that we have to design. Now, a conventional one way to do it is to do the following. Say, okay, this I know. Let me design a controller. And let me now do the multiplication, the product, to get the loop gain now with the known system and the one that I came up with. In logarithmic scale, the product is the sum. So I'm sort of summing this and this. And here I see that here is now the cross section, and I see the rate of closure, and then I see is it that this will be the behavior of the system. Now, is it good? Maybe it's not. Then, therefore, I'll go back, redesign it, remultiply it, go back here and see is it better? Is the phase margin better? So, this is a tedious approach, and I'm proposing, this is not originally mine, I've seen it actually in a very, very old paper of Bode. I'm proposing, or I'm showing here, I should say, another approach. And here it is. And it is based on the behavior of logarithmic expressions. So here I have a system. This is the system that I have. Now let's assume that I already designed the controller. For now. Later on I'll show how this approach can help to design the controller. But let's assume that we designed the controller. And we have it. Now I'm going to plot not B, but 1 over B. 1 over B. On the same graph. Okay? Now if I look at the difference between any 2 points here, this and this, or this and this, then the difference here is the 20 log A, because this is a log scale, minus 20 log 1 over B, because I've plotted 1 over B, and it turns out that 1 over B is minus 20 log 1 over B is minus B, and then the minus here is plus, and then 20 log A plus 20 log B is 20 log BA. Meaning that this distance is in fact the loop gain. Okay? It's identical, not similar. It's identical to this, except that it's not drawn with a base of 0, but it is kind of, you might say, floating here, okay? But if I've sort of pushed this one down and this accordingly, this will be the loop gain. So I have now information about the loop gain. And what I'm worried about is particularly this point. This point is when 20 log A, this is this one, is equal to 20 log 1 over B, 20 log 1 over B, which turns out that this is the point when B times A is equal to 1. So we found now the cross-section. This is, let me go back, this is the cross-section here. And we can now look at what I've defined the rate of closure to see if the rate of closure is 20 dB per decade. And if it is 20 dB per decade, then we are okay. So this method, you keep A constant, you plot the 1 over B, and you get the point that you want. So this is then, here's another example. This is then, here is the system. Here is 1 over B. Now, this is a case in which the breakpoint here is exactly where I'm crossing with 1 over B. And now the rate of closure is 20 dB, but here you see it's breaking, and the phase we know at the breakpoint is 45 degree. So therefore, this is a system with 45 degree phase margin. You can say immediately, okay? Of course, assuming that this breakpoint and this breakpoint are far away. If not, we'll have to do some more analysis, maybe simulation, to find out the exact phase margin and to do some trimming. So the point is that if I have the system, I can now, based on this, come up with controllers by deciding at which point I like to cross and what type of controller do I need in this vicinity, and also what type of controller do I need in order to get a high gain here. Because as we have said, we want for the loop gain to have a high gain as much as we can in order to make the system dependent only on the feedback and not on the behavior of the original system. So now I can get up a very general rule for different situations. I've just drawn here a imaginary transfer function for A, okay, which has many breakpoints. And the blue ones are the controller, the crossover of the controller. So I understand that if the system has a constant value here, and I have a controller that goes up like this, this is 1 over beta of the controller, goes up like this, the rate of closure is 20 dB per decade, because this is 20 dB, and this is the rate at which this is closing, and the phase shift will be, phase margin will be 90 degree. Here, for the reason that I've already said, it's going to be 45 degrees. Here, going down 20, straight behavior of the controller, it's going to be a phase margin of 90. Here again, it's 45. Here, we have a minus 40 dB per decade going down, but if the controller will also be going down 1 over the controller, so the controller itself in fact is going up. So what is really happening is I'm accumulating a lot of phase delay in the system, but I'm now providing a controller with a phase advance, because 1 over beta goes down, or 1 over B goes down, then B itself is going up, which means it's a 0, and I'm adding now a phase rather than a delay, so therefore I can stabilize the system. And then again, if there is a breakpoint and I'm going through the breakpoint, the phase margin will be 45. So this is really very simple. Sort of the conclusion here is that if I have a system and I like here to be the cross point, I need now to come up with a controller, and here is an example, that if this is going minus 40 dB, the 1 over controller has to go minus 20 dB. And this shape here enables high gain here. This is, by the way, a PID controller. I'm going to talk about it later on. I'm going to sort of unveil the mystery about the PID and to show that what it is in fact this. This is the PID. This is the proportional part, this is the integral part, and this is the derivative part. This is the ideal PID. In practice, we cannot go to infinite gain, so there is a clamping here, and also we can't go to infinite gain at high frequency, and eventually the gain goes down. But this is the portion that we are using. So this is in fact a PID. I'm going to talk about it later on. And you can see that this is very versatile, because here I'm using this part, but if I wanted to say have the cross point here, I can use this part here, okay? So this part here, in this case, all that I need is the PI controller. I don't need this part here, so I can bring this one here, cross it here. I have a controller which is here. So by this method that I'm showing, it's really very easy to come up with controllers to close the loop at a given crossover frequency and with a phase margin that we can decide on. Here it shows another example that if I want it to be at a higher frequency, then I just move this thing down. By the way, since this is 1 over, this means that the actual gain, which is 1 over this here of the controller, will be very high. It's not simple. I need now a controller that at high frequency has very high gains. And so it becomes sort of a problem. But these are practical problems of the design, but not in the theoretical point of view. So let me sum up what we have learned today. We have a known part, we have an unknown part. Here I'm just putting 1, or it could be K. This is the known part, and this is the phase of the known part. And I want to stabilize the system, and I want a certain bandwidth. So I have to add a controller, the unknown part, that will move this one up. I mean, the loop gain will be such that this will go up because I need a high gain. And when it crosses the 0 dB, I'll have a decent phase margin, so the system will behave properly. So this is the objective here. And what I've shown are the very, very basic concept and ideas that we can move ahead and see how we can actually realize the controller that will take this, bring it to here with this requirement. So this is the end of part 1. I thank you very much for your attention. I hope you found it interesting and perhaps it will be useful to you in the future. Thank you very much.